Okay, so let's start. So in the last class, we were looking at this problem of binary classification. And the way we posed it was the following. We're given two sets of points. We call it script X and script Y. And our goal is to design a linear classifier, which means a hyperplane that separates these two sets of points. So in order to be able to do so, there should exist such a hyperplane that separates these two sets. And if there exists such a hyperplane, we say that these two sets are linearly separable. So given a linearly separable class, that is two sets of points, then how do we construct a classifier? Or how do we construct such a hyperplane? That is what we were dealing with in the previous class. And we saw that this could be formulated as an optimization problem. Now the basic problem, as we saw, can be formulated as essentially just a satisfiability problem, right? After all, there should exist some a comma b such that all points in script X should satisfy A transpose Xi less than B, and all points in script Y should satisfy A transpose Yi greater than B. This problem in itself is not really a convex optimization problem. The way we had formulated it's not in standard form because we have these strict inequality constraints, but we saw that we could reduce it to just normal inequality constraints by using this particular approach. Correct. Now, of course, for such a problem, there is not a unique solution. Right? There exist infinitely many solutions if the two sets are linearly separable. So one can then think of, okay, what is the best possible solution? Is there a way of defining a best classifier? And a geometric way of doing so was to essentially consider one that is farthest away from the convex hulls of both points, right? Loosely speaking. So effectively, for any given hyperplane that separates these two sets, one could try to maximize the width or the width of this slab that separates the two sets, right? So given any hyperplane, you can construct this slab which are two other parallel lines parallel to the original hyperplane, such that all points of X are on one side of the slab and all points of Y are on the other side of the slab. So the end goal is to maximize the width of this particular slab. And we saw that this can also be formulated as a convex optimization problem, and we solved that using CVXPy in the previous class. So all of this would hold provided that the two sets are linearly separable. Now, what if the two sets are not linearly separable? How do we go about formulating this particular problem? Correct? Now, for this problem, there's not one unique way of solving it. Right? There are obviously multiple solutions, and the best solution depends on what your application is and what your requirements are. Okay. So one way is to sort of extend this particular idea of the width of the slab. Right? So given a particular hyperplane, right? So now let's look at this scenario wherein the two sets are not linearly separable. Okay. So in this case, we'll do the following. So suppose that now let's see the geometric picture. We have two sets of points, the orange points and the blue points, and the way I've drawn it, I have this green hyperplane such that most of the blue points are on one side of the hyperplane and most of the orange points are on the other side of the hyperplane. Right? So one natural way of defining the problem of the best classifier is to ensure that you minimize the you minimize the number of blue points on the other side of the hyperplane and the number of orange points on the other side of the hyperplane. That's sort of the most natural way of defining this problem. But then the problem with that is that it's now no longer a continuous optimization problem. It's a discrete optimization problem. Right? We have to count the number of points on one side and count the number of points on the other side. So that ends up being a combinatorial optimization problem, which is hard to solve. Right? So the natural problem to pose is you minimize what I call misclassifications. When I say misclassification, essentially the number of blue points on this side of the hyperplane plus the number of orange points on this side of the hyperplane. But this ends up being, this is a combinatorial optimization problem. And is difficult to solve. So let's again sort of mathematically represent what we really want. Remember, we want for all xi that lie in script x, suppose we want A transpose x to be, say, greater than b, and for all yj script y, we want A transpose x to be less than b. Okay. So let's now maybe introduce variables, right? Okay, so suppose they were linearly separable, right? The way we posed this was we essentially wanted this to be greater than or equal to b plus 1, this to be less than or equal to b minus 1. Correct? We want to find an a comma b that satisfies this. B plus 1. This can be satisfied only if it is linearly separable, right? So let's try to give, so for each point, should have been yi, right? So let's look at a natural relaxation of this particular constraint. Suppose I do the following. I have, so for all xi, I would ideally like A transpose xi to be greater than or equal to b plus 1, right? But maybe I allow some offset, okay? Maybe it's not greater than or equal to b plus 1, but maybe b plus 1 minus some ui. For each I give some sort of a tolerance, okay? So maybe it's not possible to satisfy these constraints. So I'll introduce new sets of variables plus vi. Okay. So for each xi, maybe I can't have A transpose xi to be greater than or equal to b plus 1, but it's certainly possible to satisfy A transpose xi greater than or equal to b plus 1 minus ui for some ui greater than 0, potentially greater than or equal to 0, right? And similarly for all points in script y, I want A transpose yj to be less than or equal to b minus 1 plus some vj, for some vj greater than 0. obviously if I allow any ui greater than 0 and any vj greater than 0, then it's certainly possible to satisfy these conditions. There's no problem with that, right? So if they are linearly separable, then I can choose ui and vj to be exactly equal to 0, right? But if they are not linearly separable, there would be some ui and some vj which satisfy these, correct? So loosely speaking, ui is essentially, so suppose this is my set x and this is the blue points are my set y, then each ui would essentially be this distance, right? You should think of each ui to be how far away are you on the opposite side of the hyperplane, right? So this is ui, and similarly this would be vj. Okay, so the right way of interpreting these ui's and vj's are how far away are they being from classified correctly. Okay, so we're not just counting the number of misclassifications, but we're doing something in fact slightly better. We're counting how far away is it from being classified properly.
It's modern to take. Here we are taking a straight line.
Yes.
In some other case, it would be a like parabola or something.
We're dealing with only linear classifiers here. So we want the best linear classifier. That's it. If I allowed all possible classifiers, then obviously that's easy to do.
In such a case, how would we choose one model?
So you choose the simplest model possible with the fewest number of variables involved. In this case, it's just a comma b. Sorry? There is no MSc involved here. The one with the minimum, of course, it depends on, it varies from one application to another. So that's something that as a system designer, you have to judge. What is the best possible model to choose? But in general, you always choose the simplest model possible, where you have the fewest number of free variables. And the most natural classifier that people at least start looking at is linear classifiers. Right? So we're making some inherent assumption over here. It's not linearly separable, but it's almost linearly separable.
Space, and in such a case, if we are looking at 2 or 3 parameters in the given data point, in such a case, then how like the linear classifier, like for as a hyperplane, it would be hyperplane.
Correct. That's what we have here, right? So A and B are vectors. So A is a vector in Rd or Rn, depending on the dimension of the space, and B is a real number.
But it would be too nice of an example to take.
Why is it too nice of an example?
Like, in such a case, like we are saying that the points are just separable by hyperplane. It is easily separable by hyperplane. And
correct. That was the assumption earlier, right? No, that was the original assumption, right? That they are linearly separable. Right now, we are dealing with a case where they are not linearly separable, but almost linearly separable. There exists a hyperplane such that there are very few points on one side of the hyperplane and on the opposite side of the hyperplane, so to speak. Right? That's the assumption that we are going with for now. So obviously it means that you know something about the data that you have, in which case we feel that it is reasonable to construct a linear classifier. You can think of it as a slack variable in some sense. Right. Okay. So now, well, yeah. So you can think of these as slack variables. So now, how would you pose this optimization? We built this using intuition, but what would be the formal optimization problem to solve? What would the objective function be? Yeah. Right. So one way is you basically want each of these UIs and VJs to be as small as possible. Now, in principle, you could consider multiple functions. You could say minimize the norm of UI and VJ, but we'll start with something much simpler. We'll say that we want to minimize summation I equal to 1 to m UI plus summation j equal to 1 to n Vj. Right, you want to minimize this, the sum of these, subject to the following constraints: that A transpose xi is greater than or equal to b plus 1 minus ui for each element in X, and A transpose yj is less than or equal to b minus 1 plus bj for all yj in Y. But we also need the assumptions that we also need the constraints that the UIs and VJs are all non-negative. Otherwise, you could just set some of the UIs to be really negative, and therefore that would not constitute a reasonable optimization problem. So we want U to be greater than or equal to 0 and V to be greater than or equal to 0. So we only want to count the UIs and or measure the UIs and VJs only if that point is misclassified. So this is what is called a support vector classifier. Right. Now, here again, there are multiple ways. Again, this is not the only way of formulating this particular optimization problem, and different formulations would give you different solutions. One reason for considering this simple formulation is that all of these constraints are linear. So ultimately, all you end up getting is a linear program, which you can solve using any LP solver. You can possibly try to construct more complicated formulations. For example, you want to minimize the two norm of UI and VJ. That would give you another classifier. Okay. So in some cases, it helps if you know something about the distribution or the data generation process. And depending on that, you could try to construct better classifiers. Suppose that you know that the points are being generated at random from certain classes of distributions, then it makes sense to make use of that particular knowledge to design your classifier. So one popular classifier is what is called the logistic classifier. So if you recall from one of your previous assignments, you came across the following function, which is given the following function of u. Let's say f of u is equal to e to the minus A transpose u, or let's consider an even simple version. F of z is basically e to the z by 1 plus e to the z. This is 1 by 1 plus e to the minus z. So this is called the logistic function. And what properties does this have? What can you say about f of z for all z greater than 0, or all z in R? Correct. So it varies between 0 and 1. It's always greater than or equal to 0 and less than or equal to 1. Right? So one way to interpret this is it's almost as though it's a probability. Correct. Yeah, it's sure. So let us consider the following data generation process. Okay. Wherein given any point u, in Rn. So suppose that I have two classes, let's call them 0 and 1. So the probability that u belongs to class 1 is equal to e to the a transpose u minus b divided by 1 plus e to the a transpose u minus b. Right? And the probability that u lies in class 0 is basically 1 minus this. Since this quantity is always between 0 and 1, this is a valid probability distribution. For each point u, you independently set that to be in class 0 or class 1 with these particular probabilities. Okay. So given a set of points, let's call them u1 up to say uk, you're given k points, you label them label them 0 and 1 according to the above probability. So this is the data generation process, right? But this is happening in the background. You don't really know what the values of A and B are. Okay? Our hypothesis is that somebody is randomly is taking k points and randomly labeling them 0 and 1 with these particular probabilities. Okay? All you get to see are the points u1 through uk and their labels. Okay, so you observe the points u1 through uk and their labels. Right? And your goal is to essentially compute A and B. Now, why does this particular model make sense in the context of linear classification? Let's see this particular function. What does this function look like? Right, so let's maybe just quickly plot it out. Z so it's 1 by 1 plus e to the minus z So this is what it looks like. So what is the value of f of 0? It will be half, right? 1 by 1 plus e to the minus 0, which is half. So, and if you look at this, if instead of looking at f of z, if I looked at f of a times z, right? So by changing a, you can make it look almost like a threshold function. Right? What happens if I sort of increase the value of a? It becomes sharper and sharper. Right? If I decrease a, then it becomes sort of more elongated. It's like stretching it out. Right? So if it is indeed very sharp, then it's almost like a linear classifier. Right? If a and b are sufficiently large, then so suppose I generated points according to this. Suppose I labeled points according to this, and a and b are like really large. Then it behaves then the set of points that are so generated, at least with high probability, these would be linearly separate. Correct? If a and b are really large. But if they're not, maybe they're moderately large, then a few points would get misclassified. Correct? So it kind of makes sense to think of this as this points generated according to this distribution as being almost linearly separate. Okay, that's a natural assumption to make. So you observe points according to this and the corresponding labels. Then what would be the probability of observing this set of labels for these sets of points if you're choosing them independently at random? Right? So in other words, let's say that I observe points u1, u2 up to say um have label 1, and let's say plus 1 up to say m plus n, these have label 0. Okay, remember that you're fixing a set of points and you're labeling them at random. What is the probability that this would be the configuration that you would see, assuming that each point were labeled independently and identically at random? Correct. So it wouldn't be raised to m, right? Because the probability that ui is labeled 1 depends on the value of ui. Correct? So the probability that you observe this, let's call this a configuration. Call it C. The probability of observing the configuration C, given that the points are u1 to um plus n, that is, in other words, the probability of observing this particular labeling, this is just equal to the probability, the product of the probabilities of each of them being labeled in that particular way. So this would just be product I equal to 1 to n, 1 to m, the probability that qi is labeled 1 times the product of the probabilities the probability that uj is labeled 0, which is nothing but the product I equal to 1 to m of, I guess, 1 by 1 plus e to the minus a transpose ui minus b times product j equal to m plus 1 to m plus n times what is 1 minus this particular quantity, yeah. So what is what is this probability equal to basically? Correct. So it would be e to the minus a transpose uj minus b divided by 1 plus e to the minus a transpose uj minus b. Right? So this probability assignment is for a fixed a and b, fixed set of vectors a and b. So this is given a comma b, right? So given that you observed u1 through um plus n, the corresponding labelings, then what would be the best choice of a and b? Yep. So, and why are you maximizing this? What is the principle? Okay, is this a particular principle that you have seen previously? Correct. So it's a maximum likelihood decision rule. So the maximum likelihood decision rule is you try to choose that a comma b which maximizes the probability of this particular of occurrence of this particular labeling, right? So you choose a comma b or a star b star to be equal to the arg max of the probability c given u1 through um plus n a and b. So if the data were indeed generated according to this logistic process, then this would be the best way of choosing a comma b. But even if it is not, right, even if it were not actually generated according to this process, but the points are almost linearly separable, you can use this as a heuristic. Right? You can use this as a heuristic and still try to find the a comma b that maximizes this particular quantity. The nice feature about this particular quantity is, let's say instead of maximizing this, I'll try to maximize log of this particular probability. That's what is generally done in maximum likelihood detection. This problem turns out to be a convex optimization. Log of the logistic function turns out to be convex. So you can use a convex solver in order to solve this. And in many cases, this turns out to give, so one can compare the performance of this particular classifier when compared to the support vector classifier. In certain cases, this would perform better. In certain cases, the other one would perform better. Again, it depends on how the data exactly is generated. And so again, it depends on what your ultimate goal is. Do you want to really minimize just the number of misclassified points, or do you want something more? And that depends on the application at hand. Any questions? Okay. So in general, I mean, this was of course about linear classification, but one can think about non-linear classifiers in general. We're assuming that all of these points are linearly separable or almost linearly separable, but in many cases they are not. So one can construct more general non-linear classifiers, which, so what is a non-linear classifier? So we want to construct some function f from Rn to R such that, or let me call this, such that f of xi is, let's say, greater than 0 for all xi and script x, and f of yj is less than 0 for all yj in the set y. Right. If we set f to be an affine function, then we basically get the linear classifier that we had previously. But in general, you can, unless f is even if f is convex, if it's non-linear, then you don't end up getting a convex optimization problem. So that's the challenge with non-linear classifiers. The advantage with linear classifiers is that you will always end up, you will eventually end up with a problem that is a convex optimization problem. So you can use such a solver to just solve this. You're guaranteed to that among this class, you will end up with the best possible point, right? Because you can minimize or you can solve a linear optimization problem exactly. Whereas if you have a general nonlinear classifier, you end up with a general non-convex optimization problem. So all you can hope for is to get up to a local minimum. In general, getting to the global minimum is hard. Right? So far we've seen how to solve convex optimization problems using KKT conditions and so on. And we've seen a bunch of different examples. Right? We also saw how to use CVXPy to just feed in and solve convex optimization problems. But in general, suppose you're given some kind of an optimization problem, how do you solve it exactly? We saw a little bit of that also as to how to solve unconstrained minimization problems using gradient descent. Okay, so let's revisit that a little bit and see how we can modify this to solve problems with constraints. Because right now all we know is how to numerically solve unconstrained optimization problems. But CVXPy can do much beyond that. It can solve any general constrained convex optimization problem. Right? So first let's recall different algorithms that we have seen previously for solving unconstrained minimization problems. So the first sort of class of algorithms that we've seen is gradient descent. And typically all of these descent methods, as we call them, work in the following way. You iteratively choose xt, so it's an iterative process. So in the tth iteration, you set xt to be equal to x t minus 1 plus some delta t times ut, where ut is some direction and delta t is what we call a step size. Right? So this is a general descent method. So this is called the descent direction. And this is the step size. And one of the reasons why we choose in gradient descent, we typically choose the descent direction to be the negative of the gradient. Because we know that if we go along the negative gradient, then for sure the function value is lower than what it is at the present point. And since it is lower, you can continue this in a sequence of steps. You know for sure that at every step the function value will decrease, so you can hope to eventually reach a minimum as long as the function is bounded. So we choose ut to be equal to the gradient of f evaluated at xt minus 1. But now the question is, how do you choose the step size? That's something that I've pointed out multiple times. So how do we choose delta t? One way is to choose delta t to be a constant. Right? But the constant that we choose, of course, it assumes that you know something about the function beforehand. In general, that's not a good choice. The other way of choosing delta t is to be some fixed function of t. So a kind of natural choice is to make sure that delta t is large initially and you make it smaller and smaller as time progresses. So for example, you choose some delta t to tend to 0 as t tending to infinity. For example, maybe you could choose delta t to be equal to maybe 1 by t plus 1. That is one choice. Another way of choosing delta t is, okay, so you fixed a particular direction and you know that if the function f is convex, it's a multivariate convex function, then along every direction it is convex. So along this direction you choose that step size which gives you the minimum value of the function in that particular direction. So that's sometimes what is called exact line search. You look at the function along a particular line and you search in order to get the best possible delta t. So these are fixed choices, fixed beforehand. Another way of choosing are these essentially line searches. So the exact line search is wherein you try to minimize, you choose delta t such that f of xt minus 1 minus delta t gradient f of xt minus 1 is minimized. And this is what you did in your first assignment. You saw how constant step size compares to exact line search, and in general you will require fewer steps using exact line search when compared to constant step size. But the problem with this is, okay, you're doing a line search, but in each case you will need to compute the gradient, right? And that itself is computationally expensive. It's not that we're doing this exact line search for free. There is some computation involved. So it certainly converges faster, but it's also more expensive. Instead, what many people try to do is use an approximate line search, also what is called a backtracking line search. In this case, as you saw in your assignment, you have to compute the gradient multiple times, which can be slightly more expensive. So the backtracking line search, again, it requires you to iteratively try to minimize along a particular direction, but you don't perform exact minimization. You only choose it so that you sort of have to evaluate f of x at multiple points. So backtracking line search effectively works in the following way. Suppose you fixed a particular direction. So you fix xt and a direction, let's call it u, and you have two other constants to play around with. We'll call them delta and beta. I think I call it alpha and beta, where alpha is between 0 and 1 and beta is between 0 and half. Sorry, alpha is between 0 and 1 and beta is between 0 and half. Okay. So how does backtracking line search work? You essentially do the following. You first fix delta to be equal to 1, and you essentially keep decreasing delta every single time such that it's just good enough. Okay, and what does good enough mean? So you do the following. You run the following iteratively. So you check what is the value of f of x plus delta times u, or xt plus delta times u. If this is greater than f of xt plus alpha beta delta times u, you keep multiplying. You set delta to be equal to alpha times delta. So let's look at this a little more carefully. Basically, what is this line doing over here? You keep decreasing the value of delta because alpha is strictly between 0 and 1. In every step, you keep decreasing delta in decrements, as long as f of xt plus alpha times u is greater than f of xt plus beta times delta times u. Okay, I'm sorry, beta times delta times the gradient of f at xt times u. So if u is along the negative gradient, suppose, then this quantity is less than 0, right? Because this inner product between the gradient and u is going to be strictly less than 0, right? And you choose beta and delta to be greater than 0. Both beta and delta are greater than 0. Now, we've seen previously from the properties of convex functions, if you recall, that f of xt plus delta times u is always going to be greater than or equal to f of xt plus the gradient of f of xt plus u times delta times u. So we know that for any convex function, we know that f of y is always greater than or equal to f of x plus the gradient of f evaluated at x times y minus x, right? So f of xt plus delta times u is always greater than or equal to f of xt plus gradient of f evaluated at xt times delta times u. This is always true, right? But what we want to make sure is that it's not just greater than or equal to this particular quantity. It's enough. So we want to choose this particular quantity so that it's less than f of xt plus beta delta times this, right? So basically I multiply, we want to choose delta such that f of xt plus delta times u is less than or equal to f of xt plus beta times gradient f of xt times delta for some beta between 0 and 1. Remember that this quantity is negative, right? So this particular algorithm is called backtracking line search. It doesn't give you the actual minimum what you would get in your exact line search, but it's good enough. It gives kind of a nice trade-off between a constant step size and what you would get using exact line search. In this, if you see carefully, it requires you to evaluate f of xt plus delta. So you have to evaluate the function at multiple points in each step of the line search. But it does not require multiple computations of the gradient. Okay. And in general, computation of the function is easier than computation of the gradient, because the gradient is a vector, whereas the function is just a number. So you should think of computing the gradient as computing n different functions. So this is much less expensive. So in fact, not just gradient descent, we'll see a couple of other algorithms. In each of these, you can choose step sizes based on using backtracking line search. Okay. Yeah. So the way we're choosing u is essentially we choose u to be the negative of the gradient, right? Because we choose a descent direction. So along the direction of the gradient, the function value will increase. That's for sure, right? So we always choose a direction along which the function value decreases. That's the fundamental assumption here. You always choose u such that the inner product with this is negative. Typically, you choose u to be the negative of the gradient or some normalized version of that. Any other questions? They are fixed beforehand. Yeah. You don't change them in the rest of the algorithm. Any other questions? Okay. You can have the minimum, but effectively it amounts to solving a univariate optimization problem, right? Which we have other algorithms, like for example Newton's method or the bisection method. Any such approach is fine, correct? So you can use these techniques. Right? Again, those are more, basically the point here is that those are much more expensive than this backtracking. So this would take longer to converge, but that would be more expensive in terms of computational complexity. Any other questions?
For each iteration.
So typically alpha and beta are fixed throughout, but u of course depends on each iteration, right? Because u, in fact, u depends on xt. Typically u would be equal to maybe the negative of the gradient, but this line search approach is more general. It doesn't necessarily, it doesn't have to be used for gradient descent, but it can be used for any general descent algorithm. So in fact, we'll see another descent algorithm, basically Newton's method, in which case you don't exactly move in the direction of the negative gradient. Any other questions? So maybe this is a good time for a quick quiz.